If you have ever taken a physics class, you have probably seen a graph like this one, where it shows the friction coefficient, both the static and kinetic. Today, we are going to try and measure this value for a weight and then use it to predict how far the weight will travel after we hit it with a hammer. To start with, our equation will be rather simple. We've got the tension, we've got the normal force times the coefficient of friction, and the difference between these two equals the mass times the acceleration from Newton's second law. Here's a shot of what it actually looks like getting the data collected for each of these runs. Here is the data from our first set of trials for the 5-pound weight. There are 3 trials where the weight is upside up and 3 where it is upside down. For the most part, these look similar to the graph shown in the physics book earlier. Here is a look at the mean or average values of mu, the kinetic friction coefficient, and the standard error of the mean value. As can be seen, the values for the 2.5 weight appear slightly lower than the 5 and 10 pound weights. We also see a very slight bias for the upside up estimated coefficient. In experiment 2, we'll put the table at an incline. We get an approximate measure of the inclination angle by using a tape measure and a level. We have to adjust our equation now to account for the change in the normal force. We do so by using vectors projected onto the inclined plane as usual. Again, we try to pull the weights at constant velocity to make the assumption of zero acceleration true. Here is the data from the second set of trials, where the table is at an incline. It appears that the upside up data tends to be higher than the upside down data, and the upside up data seems to have a positive slope. This indicates that despite my best efforts, I was probably not pulling the weight at constant speed. Here's a look at the mean or average values of mu and the standard error of the mean value. In this case, the 10-pound weight seems to reverse the course seen in the 2.5 and 5-pound weights, even after double checking the data. In this last experiment, we now use the measured friction coefficient with kinematic equations to predict how far the weight will travel given an initial velocity. The initial velocity is estimated by going frame by frame right after the hammer hit and comparing the distance traveled to time. Here is the data for the three hammer hit trials. The kinematic equations are represented by the curves, and the vertex of the parabolas is where the weight comes to rest, with the y-axis value the distance it comes to rest at. We can see the 2.5 pound weight has considerable error, approximately 40% underpredicted, but the 5 pound weight only has a 3% overprediction error. Finally, the 10 pound weight has about a 9% overprediction error. The results show that the friction factor can provide a reasonable approach to estimating the friction force associated with weights on a table, verified by a little experiment. Hopefully this classical physics experiment gives some insight into just how careful one has to be in basic experimentation to get some reasonable results.